We're now discussing a question 10 out of 25 on something similar to an AMC 10. Suppose that a telephone pole is 5 meters tall and it's hit by lightning. When lightning hits a pole, the pole often breaks. And this pole tips over. And it breaks into two straight segments. And the upper segment tips over and touches the ground exactly 2 meters from the base. The two segments are still attached at a point. What are the lengths of these segments? This is an example of a question where it's a geometry problem, but there is no picture. And so in order to do this question, we need to really understand what the English is asking and then draw the picture. Here, what we actually have, the pole is 5 meters tall. The pole is 5 meters tall. Let's also remember that in this problem there's a ground. And the important thing about the ground is it's a right angle from the pole. Now the pole breaks in half. And because the pole breaks in half, there's a segment which comes down to the ground. These two segments are supposed to be the same length. In what I've drawn here, they don't actually look quite the same length, and that's actually showing you what we have here, which is actually an equation. Let me try to draw it again, where they're a bit closer to the same length. Maybe like this. But as you can see, what I have to do here is I actually have to find out the sides of a right triangle. And so if I label the sides that I'm looking for, what really is happening is that that side is x, say, and this side is 5 minus x. And the information that I'm given is that this side here is 2. And so I can just write the Pythagorean theorem. X squared plus 2 squared equals 5 minus x whole thing squared. Let's keep going. So I have x squared plus 4 equals 25 minus 10x plus x squared. This is actually kind of interesting, because in this equation, x squared cancels. Usually when I do a Pythagorean theorem, I usually have a quadratic equation that I have to do something like the quadratic formula to solve. Here it's very nice. I don't actually have any quadratic at all. This is always a great surprise when you see it. And I'll say a little bit more about that at the end too. But then this becomes very easy, because this 10 goes over here, and what I have left is that 10x equals 21, and so x equals 2.1. So actually the lengths of this triangle, if I was to write them down on the triangle, are 2 for here, 2.1 here, 5 minus 2.1 is 2.9. For this 2, I'm actually going to write this as 2.0. I did this on purpose because this is actually reminding and either introducing or reminding of an important Pythagorean triple. This is the 20, 21, 29 right triangle, which is one that people don't often see. But what we see here is it actually satisfies the Pythagorean theorem. The point of this question was to translate an English problem into a pure math problem, also to see a very nice Pythagorean triple. But also there's one other kind of interesting thing here. This equation has the x squared cancel. We are very happy that we saw some very nice numbers x that came out, and we said, wow, that's a Pythagorean triple. But actually this kind of problem, if I was to change the 5 to any number I want, look at where the 5 comes in. The 5 is here. And if I change this 2 to any number I want, the 2 is here. If I change both of those to integers, I will have integers in both of these places and here, and the x squared will still cancel out. What I'm saying is that if I ask this question where I replace the 5 and the 2 by any integers that I want, then this will help me create a right triangle for which all three sides, because of the x and the 5 minus x, all three sides are rational. In this case, I took my rational numbers and I could multiply by 10 to turn them all into integers. But this interesting fact shows that you can actually create Pythagorean triples by hitting poles with lightning.